Back, we're going to go through page 12 now. Number 3, Ben drove 60 kilometres from his home to Liverpool. He stopped and visited his friend Tim on the way. Work out Ben's speed for the first part of his journey. So here's the first part of his journey up until this point. And to work out speed, we just need to know the gradient of this line. So that's the rise divided by the run. So the rise there is 30 kilometres. The run is 1, just 1 hour. So 30 divided by 1 is 30. So he's travelled at 30 kilometres per hour. How long did Ben spend visiting Tim? So he visited his friend Tim on the way. So this is the period where he's visiting Tim. He was there from 2 o'clock to 3:30. That's 1 hour 30 minutes. 1.5 hours would be a fine answer as well. Work out Ben's speed for the last part of his journey, so we need the gradient of this bit. I'm just going to draw in a triangle. Remember, this is exactly the same as doing using the formula triangle, speed equals distance over time. So the distance covered in that leg of the journey from 30 kilometres to 60 kilometres, so again he's covered 30 kilometres. The time taken was 1 hour and a half though, so 1.5 hours. Okay, so don't use 1.3 or 1 hour 30, use 1.5 because it has to be in hours. So 30 divided by 1.5 is 20. So 20 kilometers per hour. Okay, so you can see slightly less speed than this bit here, not as steep. Okay, so that makes sense with this answer. Work out Ben's average speed for the entire journey. Now, average speed is really useful because not only in graphs where we have a little stop in the middle, we want to sort of take that into account with the speed, but in reality, sections of distance time graphs wouldn't make perfect straight lines. However you're travelling, let's say by car or by bicycle or even walking, you can't just go from standing still to going at a constant speed instantaneously. What really happens is that you accelerate, and there would be a sort of curve here that would smoothly then become this line. Even if you started then travelling at a constant velocity, there would be a slight curve to begin with. And similarly, when you go from travelling to being stopped, you don't just do it instantaneously. There would be a curve here which slowly decelerates until you've stopped. So this is why average speed is very useful to be able to work out. And to work out average speed is very simple. You just take the overall distance travelled and you divide by the overall time. Okay, so I'll just write that down. Okay, so it's total distance divided by total time. Okay, so for the entire journey, the total distance covered was 60 kilometres. The total time taken from 1 o'clock to 5 o'clock was 4 hours. So the average speed is 15 kilometres per hour. And that takes into account the time he was stopped visiting Tim, which obviously lowered the average speed, lower than both of these 2 points. Number 4, Erin leaves home at 11 AM. She cycles at a speed of 16 miles per hour for 90 minutes. She stops for half an hour and then cycles home and arrives at 3 PM. Draw a distance time graph to show Erin's journey. So she leaves home at 11 AM, so it makes sense that I would start my graph at 11. And she returns home at 3 PM. So let's just see whether we can do it like this. 11, 12, 1, 2, 3. That would be fine. So I'm going to space out the axis like this. So each of the points in between these is obviously half an hour increments. Got a bit of space at the end of the graph, but that's okay. That's time, whoops, along that axis. Sorry, excuse the handwriting. Right, so She travels at 16 miles per hour for 90 minutes. So how far would she cover in that time? So that's 90 minutes is 1.5 hours, 1.5 hours. If I think about my speed, distance, time triangle, I want to know distance, so I'm going to times speed by time. So I'm going to try times 16 by 1.5, and that'll give me 24. Okay. She stops and then cycles home. So 24 miles is as far as she goes. So what could I go up in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's not quite enough space there, so maybe if I go up in 2, 10, 12, 14, 16, 18, 24. Yeah, that will do. Could go up in other things, maybe 4s and stuff like that, but this is just a bit easier, I think. You don't have to list every number on the axis, by the way. Okay, so I've got my first point. Let's put a line in. Oops. So an hour and a half, that'll be 12:30. We have then covered 24 miles. It's not going to let me do this perfectly, so you just have to bear with. Okay. Right, she stops for half an hour, so we need another line. Let's see if I can do this a quicker way, actually. And then cycles home and arrives back at 3 p.m. So a very simple distance time graph, this one. Okay, you get the idea from there. So make sure I label my axes because I'm always telling you guys to. And it's always a good idea to put the units on your axis as well. Okay, so that's miles. What is Erin's average speed on the return part of her cycle? So just the return part. So the distance covered on the return part is 24 miles. The time it takes is from 1 o'clock to 3 o'clock, so 2 hours. So the average speed there is 12 miles per hour. And the final one, a helicopter leaves Bristol at 10 a.m. I'm going to put 10 there. Flies, okay, right. Flies for 45 minutes, lands for 30 minutes, then flies for another 30 minutes. I'm just trying to get an idea of how long this helicopter's flight is. Okay, right. Okay, so maybe let's do it a different way then. Let's work out how far it goes. So it flies for 45 minutes at 80 kilometers per hour. Sausages don't talk. So distance is speed times time. So I'm going to do 80 times, and the time there is 3/4 of an hour, or 0.75. and that'll give 60, so it travels 60 kilometers in the first leg. It doesn't then travel for 30 minutes, and then it travels a further 65 kilometers. So overall, it has travelled 125 kilometers, and then it returns. So I need to go up to 125 on this axis. So let's see what I can go up in. How many squares I've got? Twenty little squares. So if I go up in tens, if I go up in tens, I can do it like this. In fact, I'm just going to write in every other one just so I can fit it on. Okay, and this is distance from Bristol on this axis. This one along the bottom is time. So, okay, so 45 minutes travels. It travels 60 kilometers. We worked that out down here. So I'm just going to temporarily go up in hours, like I did on the graph above, just to see whether it works, and I can always adjust this if need be. At 45 minutes, we have travelled 60 kilometers, so I need to go to that point there. Do this an easier way. Okay, it then lands for 30 minutes. That will be until 11:15. That'll do. And then flies for a further 65 kilometers in 30 minutes. So it'll be a very similar gradient to this one, but not quite exactly the same. 125. Doesn't want to play ball, I'm afraid. There we go. Okay, and it then flies at 100 kilometers an hour. The 125 kilometers it has to come back, so let's find out how long that takes. So the distance is 125 kilometers. Sorry, my mouse is being a bit slow. And that the speed is 100. So that gives 1.25 hours, or an hour and a quarter. We're already at 11:45 here, so it's going to get back at 1 o'clock. So I perhaps could have spaced out my axis on the bottom here a little bit more, but that'll be fine. There we go.